Today we're going to talk about the derivatives of the inverse trig functions. It sounds difficult, but mostly it comes down to just formulas. For example, the tangent function. Anybody remember what the graph of the tangent function looks like? What's the shape of it, of the tangent function? Buttons. Tangent function is made up of what? With respect to sine and cosine. It is y over x. It's the slope, actually. That's why they call it the slope of the tangent line to a curve. But it is y over x, so it's sine x over cosine x. Because it's a rational function, it has asymptotes. Where is the cosine function equal to 0? Remember, think of a unit circle. Cosine deals with the x values. When is x 0? Up here and down here. At pi over 2 and 3 pi over 2, or negative pi over 2. So these are the asymptotes of the trig function, of the tangent function. At 0, cosine is 1, sine is 0. Increasing function, it looks like this. For the domain, is between pi over 2 and negative pi over 2. The range is all real numbers, negative infinity to positive infinity. So what would the inverse of the trig function, the tangent function, look like? What happens when you take the inverse of a function? It flips around which axis? It flips across the y equals x axis. So basically what happens is your values change. Your x becomes the y and y becomes the x. So your asymptotes are here, and there's your inverse function. And remember, it's not sharing your screen? How about now? You see it now? I forgot to hit share. Sorry. It's okay. Okay. So, because when you find the inverse, the x becomes the y and the y becomes the x. So the domain of the tangent function is the range of the inverse tangent. And the range of the tangent is the domain of the inverse tangent. And the same goes for the cotangent, cosecant, and secant, because those are all reciprocal functions, and their inverses are accordingly. Remember that the inverse tangent function is between pi over 2 and negative pi over 2. And it exists where the tangent of y is equal to x. This is the same for the cotangent, secant, and cosecant, the inverse functions. This is also read as the arctangent of x. Eventually, in Calc 2, we'll do hyperbolics of these trig functions as well. Ooh, also, there's a note here that the inverse tangent of a negative angle is the same thing as the negative of that tangent function, which makes it an odd function. Remember what the odd and even functions were all about? Odd function is if you change the x from positive x to negative x, you change the function from positive to negative. That's an odd function. Remember, the secant is the reciprocal of cosine. So the inverse of the secant function, inverse secant of x, is the same thing as the inverse of cosine at 1 over x, which is the same as the shift we get from the inverse sine function. And we'll have to review the identities as well. Just look at the three identities. It all started with this. What is that? Pythagorean theorem. It defines lengths of legs of right triangles. Included in there, we can find the angles, which is where SOHCAHTOA came from. Remember what SOHCAHTOA stood for? The sine of an angle is the opposite over the hypotenuse. The cosine of an angle is the adjacent over the hypotenuse. And the tangent was the sine over cosine, or the opposite over the adjacent. Depending on which angle you're looking at. The opposite and the adjacent are either the x and the y. I'm looking for angle A. The adjacent side is my x-axis. The opposite side is the y. So y over r, x over r, and y over x, which is what our slope is all about. This same equation helped us define the formula for circles. X squared plus y squared equals r squared, the radius, which is where we then take it into trigonometry. We have x squared plus y squared equals r squared. Well, we know that the cosine is the x value, so it's cosine squared. The sine is the y value, and the radius of our unit circle is 1. So this is our first trigonometric identity. From this equation, we can do two things to it. We can divide it by cosine squared, and we can divide it by sine squared. Let's look what happens when we do both. Let's divide by cosine squared first. If we divide each term by cosine squared, simplify those. What is cosine squared over cosine squared? 1. Sine squared over cosine squared? What's sine over cosine? Tangent, since it's squared. 1 over cosine? Secant squared, right, since it's squared, it's secant squared. Here we have our second identity. The third one could be found if we divide each term by sine squared. So we have cosine squared x divided by sine squared x, sine squared x over sine squared x equals 1 over sine squared x. Cosine over sine is cotangent, since it's squared. Sine over sine is 1. 1 over sine is cosecant squared x. And that's our third identity. And I'll show you the beauty of these in a little bit. Let's look at the derivative of the inverse sine function. So if y equals sine x, the inverse is sine. Formula we used last time when we did the chain rule? Last class, what was the formula for a derivative? The derivative of an inverse function was what? The derivative, and inside the derivative you put the inverse function. We could take it further. What if we have a composite function? The inverse of the derivative of the inverse of f of u is equal to 1 over the derivative of f inverse of u, times du dx. The question is, when would you use either of these functions? When would you use the first one? If your function was just x. If it was anything else, if it was x squared or 5x or another equation altogether, then you would use the u function. So to use this with the sine function, what do we have to do? What do we need? We need the derivative of the sine function, which is cosine of x. Very good. Now we have everything we needed to find the derivative of the inverse function. So the derivative of the inverse function is f prime, which is cosine, in place of x, put the inverse function. Remember that? But we can't do too much here. Because, yeah, if this was sine, remember, the sine of the inverse function of x is x, because they're inverses of each other. So how do we get cosine in terms of sine? Let me give you a hint. It's up there somewhere. Can we solve one of those for cosine? Which one and how? Very good. We take the top one since there's a cosine. Since we know that cosine squared plus sine squared equals 1, we could subtract sine squared from both sides. And then do what to get rid of that square? Square root. So cosine is actually the square root of 1 minus sine squared of x. So this entire equation, this is the cosine's argument, the x. So we have here 1 minus sine squared of sine inverse of x. Here we have the same thing I just talked about up here. The sine of the inverse sine of x is x. Basically, the f of the inverse of x is the same thing as the inverse of the function of x. All those equal x. Compound functions. There's another rule we have to apply. This, we just did here, how does that relate to this? What can this become then? Let's see. You're close. Sine squared of the inverse of sine x is actually, since there's two of them, sine of sine inverse of x times sine of sine inverse of x, because it's squared, and this is the argument. So this one becomes x, this one becomes x, so together they become x squared. So there's the derivative of our inverse sine function. Let's do the same to the cosine function. Okay, so we're looking at the cosine function. We're looking for the derivative of the inverse cosine function. So that's going to be the same thing. It's going to be the derivative of the inverse function of x. So what do we need? We need to have the derivative of the function. What's the derivative of cosine x? Negative sine x. So it's a negative sine of the inverse cosine of x. Anybody know what that noise is? I thought somebody had a bad gas problem. Okay, so what do we do from here? Well, we'll put the negative up on top. Since we have an inverse cosine as the operation, what do we need out here to make it easier to solve? We need to have this in terms of cosine. How do we do that? From the identities. Cosine squared plus sine squared equals 1. This time, let's solve for sine, because that's what we need. If we solve for sine, it's going to be a function of cosine. So subtract cosine squared from both sides. Take the square root of both sides. So sine equals to the radical 1 minus cosine squared. Minus cosine squared of the operation cosine inverse of x. Cosine squared of inverse cosine is what? The x squared, exactly. So there we have the derivative of the inverse cosine. But what if the arguments of cosine and sine, the inverse functions, what if they were equations? So the derivative of the inverse of sine u is equal to 1 over radical 1 minus u squared du dx. Where the absolute value of u is less than 1. Likewise, the derivative of the inverse cosine of u is equal to the negative of 1 minus u squared du dx, where the absolute value of x is less than 1, of u is less than 1. What's the only thing that changes in those two? The sign. Cosine is negative, sine is positive. Let's look at an example here. Let's look at the inverse tangent, or inverse of sine of x squared. And the derivative. Use the formula we just did. What's the formula for sine? 1 over square root of 1 minus u squared du dx. What's u in our example? What's u? Because the formula was the derivative of the inverse of u dx is all this stuff. So 1 minus x squared squared. The derivative of u is 2x. Two x over 1 minus x to the fourth. And there's the derivative of our inverse sine function of x squared. It's just defining what is u. U is the argument of the trig function. Everybody good with that? Is there a limitation of what the u can be? As long as it's differentiable, remember, as long as it's differentiable in the domain, the inverse function is also integrable, or you find the derivative of it, differentiable. So as long as it's continuous in that domain. All right, let's look at tangent. Derivative of the inverse tangent of x. Start off the same way. Y equals tangent of x. The inverse of y is the inverse of tangent x. If you don't remember, then you have to use quotient rule to figure out what's the derivative of tangent. Tangent is sine x over cosine x. You'd have to do the fishy thingy. No one remembers it or has it in their notes? Yes. But for giggles and grin and to review it, let's do it again. We have the top and the bottom. So sine x, cosine x, that's f and g. The derivative of sine is cosine. Derivative of cosine is negative sine. Since this is the quotient, we subtract them. Cosine times cosine is cosine squared x, minus sine times negative sine is negative sine squared x, all over cosine squared x. Negatives cancel out, becomes a positive. Cosine squared plus sine squared is, and 1 over cosine is secant. But if you had your notes, because once you define something, you can refer back to it. But if you don't have that access, then you have to derive it again. So I said, always have a formula sheet next to you. So the derivative of the inverse of tangent, or the arctangent, we'll do it the same way. Derivative of secant squared. The x is now the inverse, which is tangent inverse of x. Remember, since your inverse function is tangent, we would much rather have the operation to be a function of tangent. So what is secant squared equal to? One plus tangent squared equals secant squared. We took the first identity, cosine squared plus sine squared equals 1, divided by cosine squared. You get 1 plus tangent squared equals secant squared. So we know that secant squared is 1 plus tangent squared. 1 plus tangent squared, and the argument is the inverse tangent of x. What is this going to become? X squared, because the tangent, inverse tangent cancel each other out. We're left with the argument. And since it's squared, we have 2 of them. Let's look at the general formula. So this is the inverse of tangent of x. That only works if you have x as the argument. But if you have a function inside the function, then it's going to be 1 over u squared du dx. That is the major argument. That's for no matter what you have. Let's look at secant. The inverse secant function. This one we're going to do a little bit different. Because of the limitations of the secant function, secant inverse of x is equal to y, correct? Well, how do we move the secant function over there? If you take the arcsecant to the other side, you get just a regular secant. Okay, if you don't believe me there, this is what you did. If you took both of these arguments and took the secant of them, the secant of the inverse secant function is x. So we just, instead of going through this whole proof, we just went, okay, we just move it over. When you move it over, you move the inverse function. Try to find the derivative of the inverse secant function. So what's the derivative of this? How do we find it? Do we use a special type of derivative? Since the argument here is with respect to y, what type of derivative do we take? Remember implicit differentiation? Whenever you take a derivative of y, you have to put dy dx after it. So, the derivative of x is 1. The derivative of secant y is secant y is the same thing as 1 over cosine y. So we have to take a derivative of 1 over cosine y. 1 cosine y. Derivative of 1 is 0. Derivative of cosine is negative sine dy dx. Cosine times 0 minus 1 times negative sine y dy dx all over cosine squared x. And sine squared y. Cosine of 0 is 0. This becomes a positive. So we have sine y dy dx over cosine squared y. So this whole thing is the dy dx. So this becomes sine y over cosine y times 1 over cosine y. Sine over cosine is? Tangent y. 1 over cosine? Secant y. This is also dy dx at the end. Did was take the secant function, convert it to sine and cosine, take a derivative of that, and now I'm putting it back in terms of tangent, secant, cosecants. Divide both sides by tangent secant y. So dy dx is equal to 1 over tangent y secant y. What is secant y? Well, let's try this. Okay, now, what is y? Y is the inverse of secant. Tangent inverse secant, secant inverse secant of x. I realize it looks horrible, but have I done anything different than I didn't do in the past? This is all algebra here, and a little bit of trig. So we know what this one's going to be. The secant of secant inverse is going to be what? That's going to be x. Secant of inverse of secant is going to be cosine squared plus sine squared equals 1. If I divide by cosine squared, 1 plus tangent squared equals secant squared. So tangent squared equals secant squared minus 1. Tangent is the square root of secant squared minus 1. The square root of secant squared of the inverse function minus 1. Secant squared of the inverse is x squared minus 1. And there's the derivative of the secant, inverse secant function. You know, it may need to be absolute all the time. But anyway, that's your function. What's the general function going to look like? And then have a du dx at the end. Secant inverse of u dx is 1 over squared minus 1 du dx. I'm pretty sure it needs an absolute value sign because it has to be x is less than 1. Y equals inverse of secant of 5x to the 4th. Find y prime. What is my u? It's 5x to the 4th. So du dx is going to be 20x to the 3rd. Look at our formula here. Absolute value of u, which is 5x to the 4th, squared, which is 5x to the 4th squared, minus 1. Du dx is 20x cubed. Do we need the absolute values now in this one? In other words, can this part ever be negative? No, because it's an even exponent. Five x to the 4th squared becomes what? Five x to the 4th squared becomes what? 25 x to the 8th. Very good. Minus 1. Five goes into 24 times. 3 and 4 cancel, so we have 4 over x times 25x to the 8th minus 1. That's the derivative of this inverse function. You have 3 x's on top, 4 x's on the bottom, they cancel, subtract them. You have 1 left on the bottom. 5 goes into 24 times, so the rest is there. Any questions so far? Because the only thing you really have to do is, once you see what operation it is, if it's secant, tangent, cosecant, cotangent, whatever's after that, that's your u. And take a derivative of that, and just plug and play. So let's write down all of the functions, all the derivatives and the functions. I was going to write them all down. Your inverse function of sine x. Let's make it u. So we have general functions. So what was the derivative of the sine inverse sine? Du dx, where the absolute value of u has to be less than 1. Get the cosine. The cosine was just the what to the sine? Negative of it. Negative 1 over radical 1 minus u squared du dx. And absolute value of u has to be less than 1. The derivative of the tangent function. One over 1 plus u squared du dx. Derivative of the secant function. One over absolute value of u, square root of u squared minus 1 u dx. Secant inverse. We didn't do this one, but and we didn't do the cotangent one. But they're similar, they're derived similar way as we did on top. So the cosecant the cotangent, that's negative of the tangent. 1 plus u squared du dx. Because the tangent was 1 plus, it's positive and negative. And cosecant is the opposite of the secant, which makes it negative 1 absolute value of u squared minus 1 du dx. Since these are reciprocal functions of the sine and cosine, Absolute value you use have to be greater than 1. There you have it. You don't have to derive them anymore. Just plug and play in these when you're given these functions as homework problems. What do y'all think? It's the end of chapter 3. It had 9 sections. It's the longest of all of them. The next chapter we do will have more interesting applications of it. We're going to look at the graphs of it. We're going to look at the fundamental theory of calculus. We're going to start driving all these further. And then in chapter 5, we'll start looking at integrals, going backwards. We only have 4 or 5 weeks left. What I'm thinking of doing then is for everybody is, since the final exams take home online, if we need extra time to cover up 1 or 2 more materials or even a review, then the day we're supposed to meet for the final exam, we'll come in here and either review or cover the last topic. But I'm going to try to get it finished before the final exam week, so you have that whole week to study, review, and everything. I'd like to try to get 1 review day in there somewhere. All right. That's it for today. We start chapter 4 next time.